Hi, I'm Robert Koenig and I'm presenting joint work with Lisa Hänggli on oscillator-to-oscillator codes. Let me first discuss two fundamental goals in quantum fault tolerance. The first one is noise reduction. This means finding mechanisms which reduce the strength or the rate of the noise. This is typically achieved by adding redundancy. A second, more ambitious goal is to make the error strength arbitrarily small. In some cases, this can be achieved by introducing more redundancy. I will call this the threshold property. Clearly, achieving this is more challenging than simply reducing the noise. You may ask if the converse is true also. For example, if we can reduce the noise level, you may be able to reduce it arbitrarily by concatenating codes. But this is not the case in general. Our work provides an example. No, Gerwin and Young have shown that oscillator-to-oscillator codes achieve noise reduction. We show that they do not have the threshold property. They cannot be used to make the noise level arbitrarily small. Let me define these notions in detail. In error correction, we encode K systems, for example qubits, by using n-k auxiliary systems prepared in a fixed state and applying an encoding unitary. This encoding is supposed to protect against noise, for example IID noise acting on each of these physical systems. To recover from noise, one typically applies a syndrome measurement followed by a unitary correction. If this recovery maps a state back to the code space, the overall effect of encoding, noise, and recovery can be expressed by a logical noise channel. This channel describes the logical error affecting the encoded information. Noise reduction is achieved when the noise strength of the logical error channel is below that of the physical noise channel. Here we can measure the noise strength, for example, by the distance to the identity channel, or the standard deviation when talking about displacement noise. An example where noise reduction is achieved is shown here for oscillator-to-oscillator codes. Let me now define the threshold property. Here we consider a family of codes and associated recovery maps. This family has a threshold property if the logical noise can be made arbitrarily weak whenever the physical noise strength is below some threshold. That is, by choosing the right code, for example one with a sufficiently large number of physical qubits, the logical noise strength can be pushed below any given noise tolerance epsilon. Here's an example of a family of qubit codes with this property. We show that oscillator-to-oscillator codes do not have this property. Before getting into this, let me clarify in what sense we may expect to protect continuous variable information arbitrarily well. For this, let us consider a classical coding problem where we try to protect a real-valued random variable against white Gaussian noise, as shown here. We can achieve the following in this scenario. For any standard deviation sigma describing the noise level, and any tolerance epsilon, we can construct a coding scheme which recovers the encoded information with distortion at most epsilon and probability at least 99%. I will use this number for concreteness throughout my talk. More precisely, we can construct a coding scheme with an encoder and a decoder such that the corresponding output random variable is epsilon close to the signal sent with high probability. Here's a corresponding coding scheme. We can just use the repetition code to create n copies of the signal. If we then have noise acting independently and identically, we end up with a sequence of Gaussian IID random variables with variance sigma squared, whose expectation is equal to the input psi. We can then estimate psi simply by using the empirical means, and this gives rise to the coding scheme. In summary, we can achieve any desired level of distortion epsilon with constant probability. Let me now discuss how we can encode quantum information into continuous variable quantum systems. On the one hand, we can use bosonic systems to encode finite dimensional systems or qubits. I call these families of codes qubit-to-oscillator codes. Important examples are the GKP codes, the cat and binomial codes, and concatenated codes such as the surface or LDPC GKP codes. On the other hand, we may try to encode continuous variable quantum information into several oscillators. One strategy for doing so has been proposed by No, Gerwin, and Young. These are called oscillator-to-oscillator codes. All of these codes achieve error reduction. If you exclude single mode codes, then these qubit to oscillator codes also give a threshold. We show here that this is not the case for oscillator to oscillator codes. To introduce these codes, let me first review some basic concepts related to GKP codes. We are going to be using N-mode bosonic systems with canonical quadrature operators Qj and Pj. We can exponentiate linear combinations of these to get the while displacement operators. A key property here is the fact that these commute if and only if the symplectic inner product of the associated vectors is integer valued. This motivates the definition of GKP codes. We can pick a set of vectors that are pairwise symplectically integral. The associated GKP code is then the simultaneous +1 eigenspace of these operators. In other words, it is a stabilizer code whose stabilizer generators are displacement operators. I recommend this reference down here for a mathematical treatment of these objects. Here's an example. If we pick these two vectors in the phase space, we end up with what I call the standard GKP code. This encodes one qubit into an oscillator. The stabilizer group of this code corresponds to a lattice, which we call the primal lattice. The dual lattice is defined by a symplectically orthogonal basis and is shown here for the standard GKP code. It is important because the volumes of these unit cells determine the code space dimension, and logical operators correspond to cosets of this dual lattice modulo the primal lattice. Corresponding displacements for logical x, y, and z Pauli operators are shown here. For a GKP code, we typically consider physical displacement noise, for example IID-centered Gaussian noise with variance sigma squared. To recover from this noise, one can measure GKP syndromes and apply a correction operation, which is itself a displacement. One simple and natural choice is called maximum likelihood error decoding. According to this strategy, one picks the displacement which is most likely given the observed syndrome and applies its inverse to correct. To illustrate these steps, we draw the lattice, the dual lattice, and the Voronoi cell of the dual lattice. This is a set of points that are closer to the origin than to any other point of the dual lattice. Now consider an error which displaces the system by a vector y as shown here. The syndrome measurement then returns the deviation to the closest dual lattice point, that is, a vector in this Voronoi cell. We can now consider all displacement vectors that are consistent with this observed syndrome. Since we are considering a centered normal Gaussian distribution of errors, the most likely error, given the observed syndrome, is the shortest of these vectors. We choose the correction to be minus this vector. The overall effect of error and subsequent correction is then given by this sum, which modulo stabilizers corresponds to a logical x error. The resulting logical error in this procedure depends on where the initial error vector lies. For example, the probability that we end up with no logical error is given by the probability mass of this blue set, which is the union of displaced Voronoi cells. We will use a similar reasoning for oscillator-to-oscillator codes, whose definition I will now review. An oscillator-to-oscillator code encodes k modes into n physical modes. We use n-k auxiliary oscillators prepared in the canonical GKP state. This is the state corresponding to a one-dimensional GKP code. The encoding unitary is Gaussian. This means it is described by a symplectic 2n by 2n matrix S, and its action in the Heisenberg picture on mode operators is fully specified by this matrix. At this point, we should consider which Gaussian unitaries are physically realizable in practice. It turns out that only those corresponding to a subset of symplectic matrices are relevant. We should only consider symplectic matrices whose symplectic eigenvalues are bounded by a constant. The corresponding quantity describes the amount of squeezing required to implement the unitary. Importantly, this measure of squeezing is non-extensive. It is the amount of squeezing required on a single mode. This follows from the Bloch-Messier or Euler decomposition of a symplectic matrix. It means that physically realizable Gaussian unitaries have an amount of squeezing bounded by a constant independent of the number of modes. This completes the description of oscillator-to-oscillator codes. It is easy to check that these can be thought of as stabilizer codes. Compared to GKP codes, we have fewer stabilizer generators and the code space is infinite dimensional. The main idea of this construction is the fact that the encoding isometry is non-Gaussian. We are using GKP states, a non-Gaussian resource. This suggests that such codes can overcome no-go results for Gaussian error correction. Such no-go results state that one cannot protect CV quantum information using only Gaussian operations, even for simple displacement noise. This is the motivation for considering oscillator-to-oscillator codes. Again, looking at IID displacement noise with a Gaussian distribution in phase space, one can recover similarly as in the GKP code by measuring syndromes and correcting. Here we again focus on maximum likelihood error decoding. We correct with the inverse of the error that is most likely given the observed syndrome. This procedure gives rise to a logical error channel, which is a displacement noise channel with associated random displacement vector x. We are interested in the probability that this logical error vector is small, as measured by the Euclidean norm. That is, for an error tolerance epsilon, we are interested in the probability that this error has norm less than epsilon. I call this the success probability for tolerance or distortion epsilon. Our main result is a bound on the success probability as a function of the amount of squeezing in the encoding unitary and the variance sigma squared, quantifying the physical noise strength. For any tolerance epsilon, the success probability is upper bounded by the probability measure of a ball of radius epsilon times the squeezing parameter divided by the standard deviation. Here we are talking about the Euclidean ball in R to the 2k and the centered normal distribution with unit variance. Observe that this bound is independent of the number n of physical modes. This implies that redundancy does not help in this setting. We cannot use more modes to achieve smaller distortion. To reach a more easily interpreted statement, recall that the Gaussian measure on a d-dimensional space has almost all its probability mass inside a ball of radius square root of d. Using this, we can conclude that if we want the success probability to be at least 99%, we need an amount of squeezing that scales as square root of 2k times sigma over epsilon. Here the key point is this 1 over epsilon dependence. Achieving lower error requires increasingly high squeezing. In particular, this implies that oscillator-to-oscillator codes do not have a threshold. In the remainder of this talk, I will try to convey some of the main ideas of the proof. The first observation is that this problem of recovery in oscillator-to-oscillator codes is closely related to a classical estimation problem, which we call partial informed unwrapping of modulo reduced Gaussian vectors. In this problem, we are trying to recover the first k entries of a random Gaussian vector from the remaining n-k entries. More precisely, we only get access to a modulo reduced version of the latter. By this I mean that every entry is only given modulo some parameter delta. The problem is therefore specified by the covariance matrix of the Gaussian distribution and the parameter delta, which determines what the estimator sees. In this problem, we are interested in the probability that the estimate deviates by at most epsilon in Euclidean distance from the actual value of the first k entries of x. Related problems have been studied in classical information theory and are of interest in settings where a signal is discretized. The quantum recovery problem and the partial informed unwrapping problem are equivalent for a certain choice of parameters and estimation strategy. This is the case when using maximum likelihood estimation to try to guess the entire vector, and then outputting the first k entries. Analyzing this problem, we find a similar geometric interpretation of the figure of merit as when decoding GKP codes. The success probability is given by the probability that a random vector belongs to a certain set. The set is defined by taking what we call a degenerate Voronoi cell, displacing it along a lower dimensional lattice, and taking the union, and finally thickening the resulting set in the remaining directions. The central object we have to understand here is this degenerate Voronoi cell. Its definition looks like that of the Voronoi cell of a regular lattice, except that the lattice spacing is 0 in k directions. We can interpret this set in different ways. For example, we can say that it is the intersection of uncountably many half spaces. Alternatively, we can say that it is the intersection of countably many sets which are bounded by quadratic surfaces. What is important for our proof is that we can give an outer bound on this set in terms of a polytope of dimension n-k. By a suitable reparametrization, we can then give an upper bound on the success probability in terms of a sum over a lower dimensional sublattice and integration over a polytope. This is essentially a convex combination. What we are integrating are volumes under some conditional distributions of balls with different centers. Anderson's inequality for Gaussian distributions states that this volume is maximized if the ball is at the origin and the distribution is centered. The claim then follows from the fact that we know the covariance matrix of these conditional distributions. In summary, we have shown that, while useful for noise reduction, oscillator-to-oscillator codes do not have a threshold unless you allow for unbounded squeezing. Finally, let me mention two open problems. Our results are restricted to maximum likelihood error decoding, a natural and efficient decoding strategy. We don't expect our conclusions to change much if we consider other decoders, such as, for example, maximum likelihood logical error decoding. But this is an open problem. Finally, and most importantly, one may ask if a threshold can be achieved with a different construction yet to be discovered. Thank you for your attention.